We move over to the last speaker of the session, and that's Paul Tadens of Sky Sails. Please go ahead.
Yes, good morning and welcome to my talk. My name is Paul and I work for Sky Sails. I'm a kite designer, but also do a lot of simulations on our kites. And today I want to talk about our coupled aerostructural model. And so currently at Sky Sails we have a design freeze of our flying system, which is good news for the control engineers because they can finally work on a constant kite system which doesn't change every month. But for kite designers like me, it's even better because we can start with a new kite design right away. And doing so, we try to use the coupled aerostructural model to help us with our design, to save time and also money. And but we have to make sure that this model is working or actually gives good results, which we had to test. So we actually did quite an extensive validation campaign for the last few months, and the results of this campaign I want to show today. So there's going to be lots of plots. And first I want to summarize a bit how the structural model works. And so it's essentially based on the coupling of two different solvers. On the right-hand side, you can see the result of our panel method. This works on a 3D kite, and so the panel method determines the CP distribution or the pressure distribution on the geometry, and then this pressure is then passed to the FEM model. The FEM model is based on a pseudo time stepping method, so it actually calculates the steady state, or let's say the force equilibrium of our kite. And when the steady state is reached for that iteration, then the displacement field is passed back to our panel method. And this whole thing is then repeated until we get a steady state, or let's say a converged solution. And yeah, by the way, if you're interested in a more detailed description of this approach, I can refer to my PhD thesis, for example, or to one of the papers. So what we use for coupling is a direct approach, so there's no damping involved, so we just take the results of the pattern method, just pass it on without any damping, without any gradient information of the change of the pressure field. This works quite well, and you can see also on the right-hand side the glide ratio of the kite over coupling iterations is plotted, and you can see this oscillatory behavior, but it usually converges quite nicely after 10 to 30 iterations. It really depends on the design. And the obtainable parameters we are using for the design is the glide ratio and the resultant force coefficient, which determine the power extraction in the end. But we can also get line forces and the stresses in the canopy. And we can also obtain wing deformation. Sometimes they are wanted. For example, if we pull or like shorten certain lines, then we can actually increase the camber of our wing. So this is really nice to be able to see this in a simulation environment. Okay, so before I jump into all the results, I would just want to quickly mention that we also made some progress on our structural solver. During my PhD, I developed this solver called mem4pi. There's also a public GitHub repository for the solver, and the problem is that it used to run in serial, so only on one CPU. And this was actually quite a bottleneck. So now you can see on the right-hand side, this is the result of a kite inflation with 100,000 membrane elements, and it took about 2 hours and 30 minutes just for the FEM solver to converge. And then I talked to some colleagues, and we actually decided to parallelize the solver. And now we use a spatial domain decomposition of the solver. So essentially, we split up the kite into smaller domains. and each CPU then can compute the forces in the membrane structure individually. And this is done using OpenMP for the element assembly. And we also had to think about a smart data structure to actually make sure that that each domain is actually able to independently compute all the forces. And so there's only communication at the end of each time step on the ghost nodes, which are the nodes touching each domain, or the neighboring domains. And I was very surprised about the results. So on the right-hand side, you can see the blue dot is the old solver. The orange line is a linear scaling, which means if you double the amount of CPUs, then you would halve the computational time. And the new solver is actually behaving quite linearly until approximately 32 threads in this case. And so in practice, this means that we can actually reduce the computation time from 2 hours and 30 minutes to approximately 5 minutes. So for me, it's great because I don't have to wait a whole day for coupling it for the FSI simulation. Okay, but moving on to our validation campaign. Obviously, we had to make a certain amount of measurements. So we use a sensor pod, which we internally call fish. You can see it on the right-hand side in the wind tunnel. This fish pod is attached below our control pod at the tether. And it also has a rotational degree of freedom, so it can pitch freely in the free stream velocity. And it has the fins which align the pod with the flow. And we also use the pitot tube to measure the wind speed. So with this pod and a load cell where we measure the tether force, we can actually determine the glide ratio and the CR. Then we also measured a lot of different line forces. So for example, we measured all the lines attached to the third rib, measured from the center of the kite. And then obviously the tether force. And we also measured the forces in the steering pulley lines. So we use a steering pulley system for our kites. So if you look from the front, then we try to use a pulley system to make sure that all the lines are in tension when we steer the kite and at the same time trim the kite. So we had to use this steering pulley setup. So we also measured the forces there. Okay, so the first thing I was actually looking into was the CR around the power trim. So on the x-axis you can see the trim, where 0 trim would be the highest angle of attack. 15% is our power trim, and 100% would be a fully depowered kite. And I just look at the sensitivity around the power trim. The blue dots are the measurements. The yellow line is the median of the bins in 1% ranges. And the yellow line, the red line is the FSI result. You can see that around the power trim, the results match quite well. And also the trend line is the same. So the slope is decreasing when you depower the kite. But only if you start depowering the kite, the CR drops much faster in reality than in the FSI simulation. Same thing can also be shown for the glide ratio. So again, here you can see the trim position from 15% to, in this case, 75%, which is depowered. In reality, we measure that the glide ratio drops as soon as we depower the kite. And the same thing can be seen for the FSI simulation. So the glide ratio drops, but it's still overestimated. So for example, the depowered glide ratio is by a factor of 2 higher in the simulation compared to the measurements. I also indicated no weight here, FSI no weight, which means I didn't include any weight of the model. I was actually running some simulations when I entered the airplane to Madrid, but I haven't included them in the plot. So I'm quite curious how the weight will actually influence the depowered state of the glide ratio. So moving on to the line forces we measured. So again, here in blue we have all the measurements. On the x-axis, I plotted the tether force, and on the y-axis, the line force of A, B, C, and D. So A is the most forward line, D is the most rearward line in a rib, and the yellow line is a trend line, a linear trend, and the red one is again the FSI simulation. And you can see clearly that the forces in A and B are overestimated by the simulation, whereas the forces in C and D are underestimated. So the kite is front-loaded, or more front-loaded in the simulation than in reality. What I find very interesting about this plot is that the behavior is actually non-linear in the simulation, as you can see, especially for C and D. So this is due to the fact that as soon as you increase the tether force by flying faster, the kite starts deforming in the simulation. And the more it deforms, the higher the angle of attack will be. So there's like a positive coupling of positive feedback, which unfortunately cannot be seen in reality. So that's a bit sad, but yeah, what can you do? The same thing can also be represented using a bar plot. So I summed up the total forces acting on this rib and divided it. So I did the ratio of each line force divided by the total amount of forces. So you can also see here in this case, forces in A and B are overestimated, in C and D underestimated. So something is wrong there, or not as physical as we hope to. So moving on to the steering pulley lines, it's actually the same thing as in the previous plots. Again, the forces in A and B are overestimated. The forces in C and D are underestimated. So again, which means that the kite is front-loaded in the simulation. And also here, using the bar plot, the same representation or the same results can be shown just using a different representation. Okay, so I showed various performance parameters like the CR and the glide ratio, and I compared them to the FSI simulation. Overall, I'm actually quite satisfied with what the CR and the glide ratio looked like, because I was not able to do this or to achieve this kind of simulation half a year ago, because depowering the kite in the simulation, it was actually quite a challenge, because I was actually moving our trimming belts in such a way that in reality, like it would move in reality, and I would always get some oscillations, and usually it would not converge, but I finally managed to get a converged result, which is nice. But as I showed, the error is actually, or the result is actually overestimating, and the error is also increasing for a depowered kite. And the forces in A and B, I mean, I mentioned this like 3 times already, is overestimated, front-loaded. And now finally coming to the culprit of this whole issue is probably the panel method. So the kite design we are using right now is, it's an open kite, so which means that we have intakes over the whole span of the kite. And so as soon as the kite flies through the air, you have a lot of turbulence. And this turbulence cannot be computed by the panel method, so it assumes an attached flow. And therefore, we get a very different pressure distribution compared to what we actually measure in reality. For me, the overestimation in CR and glide ratio is not a deal breaker, because as long as we know that it's going to happen, or it looks like this in our simulation, we can still use it. But the problem is this front-loaded kite. So we also use, for example, the simulation to estimate the actuator forces on the trim. And if the kite is fully front-loaded or like overestimated, if the kite the line forces in the front are overestimated, then you will always get very wrong trim results, trim actuator forces. So what is the outlook from here? The obvious reason, the obvious way to go would be to start using CFD, because CFD is pretty nice, because it can give you accurate results in terms of CP distribution. The problem is you're going to open up a big can of worms with that, because this whole meshing is going to be a nightmare, especially if you have a deformed kite like this, like we do. So I'm still really careful with this. The second option we think about, we are actually thinking about at the moment, is use a different profile. So as I said, our profile right now is completely open in the front, but there are different profiles in the glider industry which have smaller intakes, and they actually might be also better for our solver. So that would be a win-win situation for me. And one thing I didn't mention is the internal CP. So for example, right now we assume a certain internal CP. We actually determined this from CFD analysis, but the value of the internal CP has quite a large influence on the geometry of the kite, how it converges. So we probably have to start also another measurement campaign on this. But yeah, that's for the next months probably. Okay, and that's it. And yeah, thank you for your attention.
Thank you. I foresee a big need for a reference model and want to make a case for it, because it would be great to benchmark your solver against other solvers that are out there. And of course, that cannot be done on SkySail's commercial prototype, but it could be done on a reference kite geometry.
I mean, there's already one which I used in my thesis, so.
Yeah, that's the ram air wing of your thesis, indeed. Is your solver able to deal with the leading edge inflatable kites?
In principle, yes. Yeah.
Okay. Then we should have a word about this.
Sure.
Are there any other questions?
Thank you very much, Paul, for the nice work, nice presentation. I have two questions. One is, can you comment on that cloud of points, that you got from experiments? I expect, of course, some scattered data, but sometimes, it was really like a relay cloud. So that's my first question. Second question.
This one or which one?
Any of them,
This one,
for example,
probably,
this one.
Yeah, okay, so what you can see here is usually what we did is, so for the glide ratio, what we see is there's a lot of transient behavior going on. So for example, we fly at a constant trim, and then you can also see the median of that glide ratio is quite large, so it's like around 0.9 in this case. But you can also see a lot of data below that, right? But since the median is further up, which means all the data points below is like noise, I would say. Okay. And as soon as we start depowering the kite, there's a transient phase where the kite is actually in a transient state. And we're actually not really interested in how the glide ratio looks in that case, because we're just moving towards our depowered trim. Therefore, that's the reason why you have a lot of scatter there in that region.
Okay. And my second question is regarding your FSI model. Are you using matching grids? So like from your panel method and your structural model? Is that
At the moment I do,
okay.
But it's not necessary. I mean, you can also do like a nearest neighbor interpolation.
Okay. Yeah, you need, in that case, some sort of algorithm to transfer data from, let's say, your fluid mesh to the structure mesh, right?
Indeed, yeah.
Yeah, okay, thank you.
I think here was another, yes. You need to switch it on, just up. Doesn't work?
Nope.
What about this? Yes, okay. You mentioned that the panel method in your case cannot compute properly the flow in the intakes of the inflatable kite.
Yes.
But I think that, what about, let's say you would not have this, of course it would not be an inflatable kite anymore, but even if you had a kite with a leading edge, a close leading edge, the panel method would still not be able to compute the separation of the flow on the extra dough of the wing, because the panel method, by definition, assumes an attached flow everywhere.
Indeed.
So
Yeah.
I think the intake is a problem, but even if you solve the intake problem, you still have the problem of the boundary layer separation on the top of the kite.
Indeed, yeah. So this really depends on the angle of attack we're flying at.
And what kind of angle of attack are you flying, do you know?
Above 12%.
That's pretty high.
Yeah, indeed. So there's some separation, but that's what we have to deal with.
And then I was thinking that maybe you could model the flow in the intakes, because these are like basically pipes, right?
Mm-hmm.
You could model them in the simple model. I don't know how to do it, but you could maybe couple the panel method simulation with basically the simulation of a turbulent flow in a pipe, on which you can do an analytical model of the head losses as a function of the distance, right? This is a turbulent flow in a channel in a way.
Yeah, but the problem is the recirculation. I mean, the flow is entering the intake.
Yes?
And we also did a CFD analysis on that, and you can see that the flow is actually entering only like maybe 30 centimeter into the kite, and you have this recirculation. And everything beyond that, the
Okay.
velocity is almost zero already.
Okay. It's a tough problem.
Yes.
Thank you. Here, there's another question.
Thanks for a nice presentation. Just a curiosity. With some kites I worked with, they were leading edge inflated. When we depowered, actually we had experienced a higher glide ratio and lower lift.
Mm-hmm.
Well, here I see that you depower, you get a lower glide ratio. Can you comment what happens to the lift and drag coefficients?
So as soon as you depower the kite, both will drop, essentially. So one thing which is very important to mention here is that the line drag of the bridle system is quite large compared to the drag of the wing. So this one actually has a major influence. And as soon as you start depowering the kite, the area of the bridle system is much smaller compared to if you have a powered configuration. So therefore, the drag is also decreasing when you depower, not only by decreasing the angle of attack of the wing, but also because the area reduces.
That's
Thanks.
the difference between a ram air wing and a leading edge inflatable wing, which has much less lines, right?
I guess, yeah.
Here's one more question. Can you hand over?
Hello, thanks for your work. Can you describe a bit the method you use for the glide ratio measurements and CR measurements?
Sure. I mean, I mentioned before we have this control pod, this sensor pod here, this one. So it's essentially, it looks like a fish. It is aerodynamically well shaped, so it can pitch up and down. But as soon as you have an airflow, it will actually align with the flow. And since measuring the angle of attack on a soft kite is actually quite challenging because you don't have any proper reference. I mean, in case for let's say rigid wing, you have always the chord line, which doesn't deform, but in our case, it's actually deforming. So what we use as a reference is the tether below the control pod. And that one actually, if you have the angle of the control of the sensor fish and the tether, you can actually determine the glide ratio from that. That's how you determine the glide ratio. And for the CR, you measure the tether force, you measure the apparent wind speed, and you also measure the density of the air. And that's how you determine CR.
And in which part of the flight do you determine the glide ratio? Is it in dynamic flight or in
Also,
static flight?
It's possible in all stages. Yeah.
Thank you. I think they have already started with lunch, so probably we move the discussion to that area for the remainder. Thank you again, Paul.
Thanks.